Okay, so last couple of lectures, we covered some of the basics of the ISA, right? You will see that the last few slides in the ISA lecture, which is lecture 3, are more like, again, revision of how do you do multiply in an LU, use complement, IEEE floating point representation, some of the digital design concepts, right, that you already had in 2DI, most of them. But I'm leaving this only for your own readings, right? Just this is for completion. This is the some of the important knowledge that, for example, if you were to implement what we're going to discuss in this data path and control path in RTL, you would need to revise from 2DI to be able to implement that, right? So I skipped that. And I guess I wanted to start the topic that might be more interesting and more related to our computer architecture discussion, right? Which is we kept saying to be able to execute this ISA and to execute the program coming from the high level of the software, we need to deploy a data path and a control path, right? If you remember from our lecture 1, we said that this data path, or maybe first the control path, is the one that gets the instruction from the memory, which is what we call a fetch operation, decodes it to understand whether this is an add, a multiply, a division, and then feeds the control signals to different functional units, including arithmetic units, register file, memories, etc., to be able to execute the actual operation. And then the data paths are the function units themselves and their interaction together, the data bus and how you transfer things from the register file, right? So these are the two main distinct components. You can think of the control path as the brain, and the data path is really the muscles, right? The actual execution of the operation. Well, this is last year. I think we'll forget about this one. And by the way, how is lab one? How is lab one going? Are there any fatal issues in lab one? You guys are smiling, so I mean, this is like something good or bad. Yeah, Ajay.
Later stage runs like example 2, part 3 and 4, where Maxim would actually create like an assert error, but the TA told us we could just comment that out.
Comment that out. Yeah. Okay. So just some brief background on that. So this assertion, if you look into that line of code, is simply doing a simple check that if you have a memory operation, if this is the one that I guess you're talking about, is the one in my mind.
Yeah, it's an assertion.
Yeah, because in Maxim there are multiple assertions, but I guess this one specifically, that the one sometimes appears in lab one, is the one that does an if condition, whether this is a memory operation or not. And if it's a memory operation, then it checks that the data size inside that opcode is in fact larger than 0, because if it's a memory operation, you must have some memory operation, right? I will have to be honest. I don't understand why this is happening. I have been using Maxim for 12 years, and it never asserted to me, right? But Abdurrahman told me from last year that it has asserted for some of you and some not. And he is debugging this in the background. But the simplest format is this is just a safe check. You can comment it to continue. It shouldn't be a problem, because you will never come to this assertion unless it's a memory instruction anyway. And we're not really using the data of the opcode, just we're operating on a performance functional assessment, so it wouldn't really matter, right? So it's okay to comment it for now. And in the background, we are trying to understand what might be happening. Just to let you know, in general, especially for Maxim, which is the only simulator we use that is not developed by us, or at least in collaboration with us. But it's the one that I'm myself very familiar with. We have discovered, for example, in last year, which was the very first year that we had these labs, a couple of interesting bugs in Maxim in Lab 2, and we reported them to the Caltech GitHub repository. And last year I came to the lecture and showed them basically this is how open source code can really be developed and maintained and improved. Like we will develop it, devote the time into it. Others are using it and then find bugs, because any code would have bugs, including even industrial code, put aside open source code. And then once you find it, you think of a solution, or if you are not able to find the solution, you report a bug or an issue on GitHub, right? And then simply the team that is maintaining it will track it, will try to find the solution. Maybe when Lab 2 comes, I will leverage the opportunity in one of the lectures and show you basically the trade history of how did you find this, what was the solution we proposed, and then we also have given to the Maxim team, right? But again, that's an open source tool. The good thing about open source is, well, it's completely open, white box. You can delve into a single line of code, understand what is happening. The bad thing is that it has a limited support, right? It's not an industrial source, but I believe this is how it should be done, right? It's a learning experience. So just feel comfortable with that, right? It's not everything is perfect. Not everything is a textbook kind of equation, right? Even in industries, there are bugs and there are bugs that are even left for silicon, like because well, it doesn't work. Kind of addressing that bug, leave it there because it doesn't cause a lot of problems, right? And then issue an errata or something, tell customers that this is something that a counter, for example, that you cannot use as intended, and this is how it behaves. And that's it, right? Just again, it's just a part of a practical engineering experience. Is there any other logistical or technical issue than this assertion? Yeah. Yeah. Are we creating a lot of debug files, I believe, especially for lab one, right? And this is why I believe Abdurrahman might have guided you to write some scripts to automate that process. Well, my suggestion is once you extract that, we're not asking you to really upload or push these files to the repo, right? So you only extract the meaningful information out. My suggestion, if you're writing a script, just auto remove these files after you do the processing. If not, then manually remove them. But in reality, once you run an experiment, you create the files and then you process them. You no longer need them. Just don't keep them, delete them, right? In subsequent labs, we'll not need that much space, but especially because we're doing some performance, a whole application assessment in lab one, that might be a necessity, right? Yeah, Arjun?
No password so we can install or other things that
on the VM?
Yeah.
Oh, you guys are not given, like your user is not a root user? That's a very interesting point. I thought all the groups created by the TAs are in fact root in the VM.
It would be really great if you just post on the classroom. Then if people want to use it, they can. If they have no reason to use it,
yeah, there is only one. Well, the only way to do it safely. Well, you can imagine why you are having a separate user for each group, right? Because this is basically the lab machine is a shared lab machine, and you don't want others to access your code that you develop in the lab, right? But one way to address this is we have to go for every single account created on the VM and make it root, right? We cannot basically give you one account where it has the password because anyone will be able to access. So it becomes a shared space at the moment, right?
Yeah, but if all our development's being done in GitHub, then I don't understand.
Yeah, there are things we can control and there are things we cannot control, right? I mean, aside from GitHub, what I mean is that the actual lab machines, right? These are supposed to be shared lab machines where anyone can access, right? And you go to the lab and access any, and if you have the password for the VM in that lab machine where the other group basically develop their own lab solution, then you'll be able to access that lab solution, right? Well, the counter argument is, well, internet is very big, right? We have GitHub and we can share code in the background, but that's something outside of our liability control, right? So we are asked by the IT in the department to maintain separate accounts for different, well, lab groups or whoever is submitting the lab, because that's something as part of the liability of the department. Outside of this, it's just left for your own honesty, right? And the integrity. But I do understand the need for this. It's a necessity. It's very important because you'll be able to install tools. We'll have to find a way to do that.
It's mostly for, like, realistically, I don't think a lot of people need to install stuff in the lab. It's more like
that's true, and in fact, that's one of my intentions, to keep it distributed and decentralized. You can really work at any. And for your laptops, I guess that's something. Yeah, we can try to do that. Yeah, I just have to think of all the consequences of that. Yeah. Any other? Last year there was some complaints about like writing scripts, and maybe this is the first time you interact with Shell or something. But you don't have to write scripts in Shell. This is something to help yourself, right? You can write it in Python, in Perl, in anything, right? That's part of a process automation. Starting from lab 2, we already give you some of those scripts already ready. But I guess it's a good exercise in lab 1. I guess Abdurrahman also helped a lot of you creating some of those scripts that they had questions. But I'm not imagining you can do it manually. Well, you can, but you'll spend a lot of time, right? So you don't have to do that, right? It's anything that can be automated. As an engineer, think in that way. Anything that can be automated, invest the time and automate it from the beginning, right? Because it saves you a lot of time. Okay, so hopefully you're not facing a lot of issues, because this is something orthogonal to the actual technical topic of the lab. It's a good engineering exercise, right? And if you had questions, come ask me, come to talk to the TAs. But it's a good taste of a tedious task, a repeated task that you repeat a lot, and then it's just ideal for automation. Okay. Okay. So now we go back to our topic, which is data path and control path. I always want to keep that big picture here, where we keep saying what type of the system we are covering at the moment. We will stay for quite some time on the CPU, for the control path and the data path and the pipelining and out folder, etc. Then we'll jump to the memory. We'll talk about caches and DRAMs, and at the end we'll come back to the CPU, talk about more advanced topics. Okay, so here we're throwing in this picture where it's a very high level view of a single cycle. Well, it's basically a single cycle, non-pipelined processor that simply tries to achieve or tries to execute the ISA we have discussed in the last lecture. So what is our goal here? Our goal here is, after we understood the ISA, the MIPS ISA, the simple one that we have covered in the last couple of lectures, we opened the manual, we understood them, we'll start to think of how do we implement them. Ideally, you take it all the way down to really RTL implementation, right? But as we said earlier, this is a topic for a different course. It's computer organization course. And I highly encourage any one of you that has some time and is interested. There are multiple projects. I can even give you some hints, some pointers that you can go ahead and implement this in RTL. It's a very, very good exercise. But it's a topic that is lower level than computer architecture that we want to focus on, right? In other institutions, as I said earlier, there are a couple of courses that are built on top of each other. You first teach this very basic one in the whole course, and the lab is purely RTL implementation of a single cycle processor, pipeline processor, etc. And then in a computer architecture course, we go to the advanced topics like caches, advanced out folder execution, etc. But because I'm trying to combine this knowledge in that single course, then simply we'll go through control path and data path in the high level, try to understand it on slides. We don't have a lab to implement it ourselves, but you can go ahead and implement in RTL if you have the time. It will give you definitely a better and more hands-on experience. And also in the simulator, you can check how Maxim does things, right, in the execution path. Good. So if I'm building the machinery, the circuit that tries to implement the ISA in a non-optimized format, what do I need? Well, we talked a lot about a program counter. That is a register that holds the address to get the instruction from the memory. Good. Which is the very first part of the control path. I need to bring in this instruction from the memory to the actual processor execution, right? So the program counter is the first thing you will encounter here. There is some circuitry. If you remember this one, can someone tell me from our last lecture what is that part of the circuit is? This one here. So why do I need that part? Yeah. Yeah, the jump and the branching, right? So because with a program counter, usually you increment by 4. But if you have a control instruction or control flow instruction, like a branch or a jump, then simply you need to add some extra logic. You need to load in the offset or the address into that, right? And well, I only do this for a branch or a jump instruction. That's why we need some enable here that it will come later on. But that's as a whole the part of the circuit that tells what program counter next I need to read. It's either program counter +4 for the next instruction, or well, my jump address or my branch address if I have a branch that is sticky. Good. So I do this to bring in the instruction from the instruction cache. So this $sign thing is our instruction cache. What is an instruction cache? You can think of it as just your memory to bring in the instruction from, right? But for optimization, almost all current modern processors have a small L1 level 1 instruction cache that maintains the most recent, well, cache lines that you access from the instruction, right? From the instruction code, simply to fasten or to, well, improve the performance of fetching the instructions. Because if you cannot read a new instruction every cycle, everyone else has to wait, right? Fetching instructions from the memory is in your critical path. That's what you are going to operate on. If you don't have an instruction, you cannot do anything, right? So this is the part that you want to really maximize as much as you can. Good. This is why we have an instruction cache. So I use the program counter with whatever its value is, whether it's program counter +4 or my new program counter for the branch, as an address to go to the instruction cache to bring in a new instruction. Now I brought in an instruction that simply I need to understand what this instruction is, right? Who is helping me with this? It's your control path. Right now we have the control path simply as just a red black box, a red box that is not simply, we don't know what is inside. We will come into this in a separate set of slides. But the idea is I do understand what is once I go out of this control path, I do understand this is an add operation. I'm operating in R1 and R2 as reads. Then I'm going to write the result in R3, for example. And once the control path does this decoding, it enables simply all the reads and writes and execution units to achieve this add. So you find that there are signals going out, these red arrows here, going out from the control path to the register file to read your operands, for example, enable the ALU to perform the operation, and then enable either the register file back to do the writing, or if this is a store instruction, you have to enable the data cache, your data memory, to write the store instruction in. Good. So anything here, any circuitry, any functional unit in your data path is controlled by the control path. Right? And so why there are red arrows everywhere, even for the selection lines of the multiplexers, for example. Questions, please? Yes. Well, you mean in real hardware or in that diagram? Yeah. Yeah, in that diagram, simply, well, aside from how it's being laid down in the actual chip, you basically have your pipeline logic, right? Your actual data path and control path. And then simply you have an address register, like a program counter in case of an instruction, that gives you an address that you go to a memory. This is basically your L1, right? Well, if this is an instruction, usually L1 is a split cache, instruction and data, and this is something we're going to discuss in pipelining. So we're talking about an instruction, so you have to go to the instruction cache with the program counter and bring in the new instruction. So where it's being in our logical view here, it's simply during the fetch unit, right? So simply, it will come later on that we have, well, we can abstract this into a fetch stage, a decode stage, and then an execute stage. I bring in the instruction from the memory, I decode it, and then I execute it. In that logical view, what do you think the L1 is? In which stage of these? In the fetch stage, exactly. Thank you. So this is basically what represents your fetch, and the decode inside the control, and everything else is the execution, right? So that's in the logical view. Does this answer your question? Any other question? Yeah. Yeah, but not all of them, right? Because it's a small cache. Maybe your program is very large. So usually if you don't have an instruction cache, all your code will reside in the main memory, right? But because you want main memory access time is very large, you want to increase the performance of your program execution. So you bring a bunch of instructions, place them in the instruction cache, and then simply execute from them, hoping that you don't miss in the instruction cache. Because the instruction cache access time, for example, is a single cycle in most modern processors. So while main memory access is 100 cycles, right? So it's a way to improve the performance of your instruction fetching from the memory, right? But it cannot hold all the instructions because it has to be very small, right? We are going to discuss caches in a very detailed lecture, right? So it will come later on, but that's the main concept, is because I don't want to afford the high cost of going to the memory every cycle, to the main memory, to the DRAM. I want to build small caches in my hierarchy to fetch data such that I read it faster. Sense? There was another question. Yeah. Oh yeah, I guess maybe you missed my statement at the beginning of the lecture. Yeah, I wasn't able to upload it. I don't know why. So I will retry after go to my office, but it is not currently on Avenue, right? That's Yeah, thank you. Any other question? Yes.
Does it getting new codes to implement, or does it get set at the beginning of the program and all those codes that are still there?
That's a good question. That's a good question. So again, the details of how cache gets its data loaded from the main memory is a topic that is evolving, and we're going to have cache lectures separately. But you can think of it as at the moment is the following. In the very first time you want to read an instruction, initially the cache is empty, right? We call it a cold mess. There's nothing in the cache. You go to the main memory, but you don't bring a single instruction. You bring a bunch of instructions loaded in the instruction cache and then keep reading from it, right? And then every while you might miss in the instruction cache, right? But even with this, there are, and this is a topic that you're going to have in your project, even you want to, you don't want to miss at all in the instruction cache. So what we do is we don't wait until we miss in the instruction cache and go to the main memory. We build something we call a prefetcher, where in the background, while you are reading from the instruction cache, proactively you bring in new data from the main memory loaded, such that next access is also ahead, right? And this is called instruction prefetching. It's very, very successful piece of hardware currently. Like you can think of an instruction cache access like hit rate. What we call in cache is hit rate, means how many times you find the data you're looking for in the instruction cache. It's currently 99.5%. So almost I will never go out of the instruction cache to go to the main memory. Again, we're going to discuss this in a bit of a detail, right, later on. Other questions? Good. Great. So think in your mind about these logical 3 stages, right? The sequential stages. I fetch the instruction from the memory. I decode it to understand what it needs to do. And then I enable the execution units to do the actual execution. Good. Now, we're going to take every single type of instruction. Ultimately, if you are building that processor, you will take every single instruction in your ISA and think of how do you really implement it in a detail in your data path, right? But because of the time of the lecture, we're going to pick the ones that are going to cause interesting discussions in the control path and data path. For example, if we implement an add, implementing a sub is exactly the same, except that your selection line for the ALU is for subtraction instead of addition, right? So it's just almost exactly the same. This is why we pick the add among the arithmetic instructions. And then we pick the add I to also see how do we implement, because immediate values are a little bit different, right? So if you remember, add I has its own type of an immediate type instruction, right? So it builds a category of a different instruction. And then we pick the branches and the jumps, because again, they are unique, and then loads and stores, because these are memory types. So you think of, we have picked from every type one example interesting instruction, and we are going to discuss how we implement it in our control path and data path. By the end of doing this, you have a simple processor that implements this instruction, but in reality, it would also implement the full set of the MEPS ISA that we had in the last lecture. Good. So you see the flow that we're going to go through, right? This is in every set of slides, we take one instruction, think of how our control path data path signals are going through to execute that operation. Good. So before delving faster, I keep saying there are function units. You guys got introduced to ALUs in your 2DI, but what is a register file? I think you might have interacted with the register files in 3DQ, for those that took 3DQ. Simply, a register file is a bunch of registers. You can look into them logically as one set. Sometimes they're implemented as real registers, sometimes they're implemented in FPGAs as block RAMs, right? But you can think of it as a simple memory that has some locations. In our MEPS ISA, we have 32 locations, and there is a data bus and there is an address bus. Well, there is in port and output port. In our case, if you remember, we said register file implements 2 read ports and 1 write port, right, from our last lecture. And then we have the address to address one of these, excuse me, to address one of these registers. So our logical view will be, well, I have a write port, which is a data basically. I have a read port 1, read port 2, which are also data. I have an address. And then I have a write enable simply. And because this is a register, you also have a clock, right? Because we overlook this, you can have a reset and these type of things. So again, last lecture we discussed why we need two read boards and what is the trade-off, right? Most instructions have two read operands, so it will make it faster. Why only one write board? Because at maximum, one instruction would have a write board, would have a write operand, a single write operand. Then you have the address to read this. Now let's discuss a little bit, given our MIPS ISA, what is the width of every one? First of all, our address, if I have 32 registers, how many bits do I need for the address? This we already said also last time, we need 5 bits, right? So you have 5 bits for your address. What about data? What would be the width of our data bus for the register file? Yeah, 32-bit, thank you. Because our registers are 32 bits, and we're going to either read those registers or write into them, right? So your data bus here is 32-bit, right? And basically your write enable is a single bit, your clock is your clock, right? Good. So this is simply how we are interacting with the register file. Good. For the memory, so for register file is one of our state keeping function units. Memory is the second state keeping function unit. Memory has an address bus, data bus, just a very abstract view, a write enable as well if you're doing the store. And then simply the data bus, you can have a separate read and write, right? Or you can have really a unified in-out data bus, right? Here we're assuming you have data in and data out, right? So here if you're reading from the memory, here if you're writing to the memory. What would be the address of your memory in our machine? The width of the address? Do you think? What do we use to access that memory? Let's say this is your instruction cache that we discussed. Yeah. 64 is in modern machines. That's true because your registers are 64, right? But the MIPS instruction, the simplified one we are covering in these lectures, what is the width of the registers? 32, right? So every register in our machine is a 32 register. And this is in fact a very good discussion. Old machines, they used to be what we call them, there is a technical terminology called the machine width, right? When you hear this word machine width, we are referring to the width of the registers in the machine, right? Old machines used to be 32-bit machines. I don't know if up until now, if you try to install an operating system, did you observe that? Do you have the 32-bit version or the 64-bit version, right? Because 32-bit machines, in fact, have been common. My first 2 computers were 32 bits, right? So all registers in that machine are 32. This is what we call what we mean by a machine width, right? And if we want to go to a memory, we are using a register to address the memory, right? Whether it's data or an instruction. If we, in case of an instruction, what register we are using to access that memory? What is the name of the register that holds the address to go to the instruction? Yeah, the program counter. Thank you. And if it's a data memory, remember our load and store instructions also are written in something like this. We had that example last time. And we said we read that register, we add the offset, and then we use it as an address. So you still take your address from a register. So if your machine is 32-bit, then your address to the memory must be 32-bit. Right? What is the limitation of this? If you have a 32-bit address to a memory, what is the maximum capacity you can cover? It's 4 gigs. 4 gigs, right? 2 to the power 32 is 4 gigs, right? Which means in reality, 32-bit machines cannot afford our modern DRAM physical memory address, right? So basically, your maximum limit is 4 gigs, and this is why there was a strong need for expansion of going to 64 bits, right? But the one we are covering is 32, which means our address is 32 bits. What about our data bus width, data in and data out? Also in the machine we are covering, not in modern machines. Think of what we are writing to the memory and what we are reading from the memory, or where do we store the data we get from the memory, and from where do we need to read the data that we're going to write to the memory. It's all also in registers, right? 32, exactly. Thank you. So again, you are reading data from a register to store in a memory, or you are reading data from memory to write to a register. And our registers are 32-bit, right? So your data in is 32, and your data out is 32-bit. Good.
You said that the limit for 32 systems is 4 gigs. That simply means that the system would be unable to address more than 4 gigs worth of memory.
True.
So the rest of the memory would effectively be unusable.
Yeah, which means there is no rest of memory then, physical memory, right? There is still the virtual memory concept that I hope we spare one lecture to talk about, but physically you cannot address more than 4 gigs. Yeah. By that time, DRAM was capacity was lacking behind, right? So those who own 32-bit machines like 15 years ago didn't have even in the market 4 gigs of RAM to be able to put in, right? So it wasn't really, but then things started really ramping up, and then you face the limitations of it. So it wasn't a very real challenge, right? But right now you cannot imagine having a 32-bit machine that only addresses 4 gigs of RAM, because our phones even have larger memory. Any other question? Good. So now we defined our interface of the register file and our interface of the memory. So let's go through abstractly before starting the instruction by instruction case. Let's get to the common operations we have to do for regardless of the instructions, right? Regardless of your type of the instruction, you must fetch that instruction first, right? Whether it's an add or branch or store, I don't even know that it's an add or a branch or a store until I fetch and decode it, right? Which means the front end, what we call the front end of the processor pipeline, or the front end of the processor circuitry, is just common across all instructions, right? So the fetch stage, you have to fetch any instruction first. And our fetch simply, if we ignore branches for now, is composed of a program counter that once we read, we increase by 4. If we don't have any branches, right? We just go sequentially. And I use the program counter to access the instruction memory to obtain the instruction. That's simply your fetch. Good. Now, once I fetch an instruction, I want to send to the control unit, right? The control unit is going to simply decode its different fields. Assume we have something of an R type, like something like the add, for example. Then the control unit will take the opcode, determine the function of the instruction, and this function, there's some circuitry built that we are going to look for in detail later on. But simply use these bits to drive, for example, you determine this is an add, then I need to enable the LU for an add. And then I need to send the 2 source registers, the operands, to source 1 and source 2 for the register file for reading. And then I send the address of the destination register to the actual, to one of the destinations of the register file, which is our write port address, right? And then simply, once I do the operation, you read first from the register file, you execute the ALU, and then you write the result back. This is basically your write board for the register file, right? So these are your 2 read boards of the register file, because you need to read 2 registers to execute the addition. And once you obtain the result, you go ahead and write it back to the register file. Good. So this is simply your decode and the execution stage. Good. Now, if this was an add, then again I have 3 addressees of registers, 2 operands input and 1 operand out. If this is an add I, things are a little bit different, because if you remember add I from our last lecture, we add an immediate value to a source register and take the result in the destination, which means we need to read only 1 register, not 2. But I have to get the immediate value from somewhere else. From where do I get the immediate value? From the instruction itself, because we encode the immediate value inside the instruction code. So right now, the decode unit will behave a little bit differently. It will take the immediate value and then simply feed it to one of the sources of the ALU, to one of the inputs to the ALU, right? And then it will take the source, which is this one, RS1, and go ahead and read it from the register file and send it to the ALU. And once you are done, you store your result back to the register file in RT address. Good. which means in our case, for the add-I instruction to the register file, you need to send the source address, the destination address. Good. And then you need to read the immediate value from the ALU and then sign, extend it, and send it to the ALU. Right now, I have this red block here, which is just a simple multiplexer. Why do I have it? Because if you go one step back, if it was only an add instruction, it's just very simple. If you are building a processor to only doing this instruction, what I'm going to do is send your two source operands to your register file, read their data, do the addition. So you directly read the data, do the addition, and then obtain the result and write it back. I'm done. But if I want to support a processor that has the two types of operations, add and add-I, right now the ALU, well, it will still, in both cases, it will still need to read one source from the register file, right? But in the second source, it can either come from the register file in case of an addition, or from the immediate value in case of an add-I, right? So there are two possibilities here, and that's the reason for this multiplexer here. In case of the add operation, I'm taking these two paths. Maybe I should use two different colors. So this red one is the add case. While let me just try to figure out how do I change the color. So let's do this. In case of the add-I, well, so this thing here. In case of the add-I, I'm doing this, but instead I'm doing that path, right? It's become very crowded at the moment. So I have two possible paths based on the instruction, type. If I have an add, two sources come directly from the register file. If I have an add-I, one source comes from the register file, the other one comes from the immediate value. So I need a mux. What would be the selection of this mux, logically? Yeah.
Select from the immediate data, not from the register, because there didn't be anything from it.
Yeah, for this type of instruction, right? True. Like basically for the add-I, you have to do the selection such that you go for the second option here, right? But if you have an add, you need to select the first one, right?
Well, you're saying this infrastructure always exists.
Exactly. So we're building it one by one, right? So this is our rationale. Maybe also I should explain this. While we're going and building this, we'll start by building one instruction at a time and add circuitry to our datapath and controller path. So if I'm only doing an add, I have that. But now I added an add-I on top of an add. If I only have an add-I, then I will not have that mux, right? I will just directly go to that path. But I want to support two types. The processor wants to support two types of instructions. It's why you would have that infrastructure always. But then you need to drive that selection line to tell the ALU whether you should pick from that or from that. Yeah.
To get driven by a bit in the opcode.
Exactly. Thank you. So the control unit, based on the opcode and the function, will drive that bit because the control unit is the one that knows whether your instruction is add or an add-I, right? So if it's an add instruction, it will set the selection line to 0 to pick the first path here. Because that's basically a 2-input multiplex, right? It's a 2-to-1 mux. And then if it was an add-I, then you have to select the second one, so you set it to 1. Good. Questions? Yeah.
So mux into the D. What's that?
The D input.
See how there's a mux that takes the RT and what looks like the immediate.
Yeah, that's a good point. Well, that's a very good point. In that case, we have to put these two together. So I will write this down, but let's go through that R type, the normal add operation. You have the opcode and the function here, which are fixed. Then you have RS, RT, and RD. RD is your destination, correct? And RS and RT are your sources, right? So now if I go here, and I will try to write the R type, the op would remain the same. I have some bits for function here. RS remains the same, but then what did I have here? It's the RT, which is the second source. And then I have the destination here. So now, if you are the control unit, you need to also tell the register file from where do I need to read my sources and destinations, right? If it was an add, I'm reading my first source from here and my second source from here, right? Because this is our add opcode. It's RS, RT, I should write it fully, op and function, right? So if you were an add, my first source will come from this set of bits, right? And the second source will come from this set of bits. And then my destination will come from here. Good. In case of an ADI, well, the first source is the same. This is why we don't have any mux or anything, any circuit in this. It's just always this thing, right? But now, if you think about it, these two types of instructions differ at the moment. For an add, this field represents your second source. For an ADI, this represents what? Well, if this is the add, so it represents your second source. This one represents your destination for the ADI, right? So now you need to detour this one to go to the destination instead, right? Because you changed the locations of the fields in the instruction code. That's why you need to say, well, this one is simple. I'm always reading first one from here. If I had an add instruction, I'm always reading this into source 2. But if it was an ADI operation, I need to take this and in fact feed them to the destination. It gets it to both, but in reality, there is a mux here also that determines whether, because if you think about this destination, it either takes from here if you are an ADI or from here if you are an add. So it takes from two different places, right? And this is why you need a mux. And again, the mux is driven exactly by the same logic as this one. If it's a 0, it's an add. If it's a 1, it's an ADI. Yeah. Hand raising here.
No.
Good. You got it? Yeah. Makes sense? Now there's a question. Why I'm always feeding this to the S2 if I'm not using it in the ADI, right? Because you are not going to read. Reading from a register file, it can just remain floating. The problem is with writing. You don't feed the right enable, right? So instead of adding a mux here and complicate your circuitry, well, read enable is like, it's just there, right? So you feed an address, but you don't get something out. And if you get something out, you are not using because the mux will be this one anyway. So it will just remain unused, right? Good. The problem is with the destination because the destination has to get it from two different places and the destination is used in the two instructions. Things started becoming a little bit complex, but low-level digital design. So if you have questions here, ask, because we will keep building on top of the circuit. It becomes more complex and complex and complex, right? Good. Again, the philosophy here is we support one instruction type, simplest circuitry, and then we start complicating it to add more support. Good. Questions? Good. So now we go to the memory type. I want to support a load operation. What do I do? Well, I first need to remember from the previous lecture, what do we do for a load, right? In case of a load, you have a load instruction. You have simply a register that you use for an address. You have an immediate offset that you add to this address. And then you have a destination to put in the result that you get from the memory. So simply what does this do is there is an immediate value offset you add to your source, RS. You go to the memory with this address, you read the data that you write into RT, right? This is what the load will do. It's very important to start with this because this is what will drive what control signals you have forward, right? So for example, once I fetch my instruction, I do understand it's a load. What do I need to do? Well, look for your sources because the first operation is to read the source. So my source, well, I look into the I type, I find my source also in the same place. So that's simple. I already had the circuitry from before. I'm not doing anything. Good. You'll observe that whatever we add newly is going to be in red, right? So anything else is just green and black. So this was there before. I'm not doing anything. Then once I read that one, I need to add it to the immediate value. From where do I get the immediate value? Well, again, from my instruction, right? So I take the immediate value, sign extended, and you can observe that our load is in fact of an I type, right? Or loads and stores, which is also the immediate value type that we had earlier. This is why the changes are minimal. So I sign extend the immediate value. This is SX block here, sign extension to 32-bit, and then read the RS, add both together to form the address. In case of an add and add-I, once I'm done with the add operation, I'm done with everything. I just write it back to the register file. In case of a load, it's not the case. Once I calculate my address, I have to go to the memory and get some data. That's why we add the memory here. You go to the memory with the address you calculated, you read the data from the memory, and then you write it to the register file. Where do I write it to the register file? Here comes my destination. which also comes from here, right? And you need to also drive the right enable of the register file to be able to write. Good? Makes sense? Great. So now, because your destination to the register file now has two different paths. If in case of an add and add-I arithmetic operation, it comes directly from the ALU, right? If you go back here, it comes directly from the ALU. In case of the memory instruction load, it comes from the memory. So it comes from two different places. I need a mux. So we add a mux here saying, take the direct output from the ALU or the output from the memory and add a mux. And this mux is going to be your destination to the register file. Good? Yeah. RS. Oh yeah, okay. I'm reading RS from the register file. Our registers are always in the register file. I'm reading the value of RS and then use it as an address to go and bring in a data from the memory. This square brackets means use this as an address, go to the memory and bring in a data from the memory. This is why I'm always reading from the register file. But then after I do the add operation, which is this one, take that as an address. This is your address port of the memory. Read your data and feed it to the register file. Okay? Now for this selection line, what do I select? Again, the control unit is the one driving it. If it's a load operation, I have to select the second one. If it's a store operation, if it's an add or add-I operation, simply it comes from the first one, right? Good. So this selection line again is driven based on the opcode of the instruction.
Are we like currently ignoring that the data transaction could take a long time?
Yeah, 100%. So this, in our discussion of control path and data path, we're assuming this data memory is just access to while you're doing this. One reason why this is valid, because we never discussed how many cycles I take here. It's just, we say this is a simplest single cycle processor where you take all the time you need to bring in your data, right? We didn't even discuss pipelining, which means if the data here takes 100 cycles, I'm just waiting, right? Like until I bring it in, because we're executing one instruction at a time. This becomes a little bit complicated when we discuss pipelining. There is a control frequency, and then if I have a data mess, what are the consequences? So we go to caches, right? But that's step-by-step discussion. Here, any function unit takes whatever time it needs because I just have a pure, I wouldn't say combination because there are sequential elements, register file and data, but I am executing a single cycle processor where you take all the time you need. Frequency is not a problem. Okay. That's a good question. Any other question? Yeah.
So right now, all the muxes are being driven by the opcode. And is it so? Are each of the muxes driven by one bit in the opcode, or is it? Like how does that work?
Yeah, I guess you are referring to the selection lines, right? Because for example, this mux, its inputs are the destination register, and this mux is so. Yeah, most of the selection lines will depend on what instruction I'm executing. So in the control, yeah, exactly. Like the control is the one that feeds all these selection lines, all the enables, and from which you should read, right? Yeah.
But then is the opcode limited to only have 6 muxes, or that can't be the case?
Well, oh, that's a good question. If your opcode is 6 bits, it doesn't mean that you cannot, well, because you can have multiple really logic on top of it, right? Because some, for example, this mux, if you think about it, this selection line is going to operate that way, whether you have a load or whether you have an add-on, right, or other type of immediate instructions. So there must be a logic layer between the opcode and the selection line. And we're going to have this discussion later on, but there is usually you build a ROM or you build a combinational logic that takes the output as an input, do some circuitry, ands and ors and muxes, and then feeds selection lines there. The decode unit is one of the most complex in modern processors because there are so many instructions and you have to optimize it in a way. Yeah.
Trying to understand it because you're saying immediate plus RMS. Does that place in memory and store to RFP?
Yeah.
So RT is in memory or?
Yeah. Okay. So let me revise a little bit what we have done with the load instruction last time, right? So you have your memory, you take an address, and you read a data in case of a load operation. In case of our load, this address is exactly this one. And the data you read is you're going to write into RT. So RT is your destination register, right? That anything that has a dollar sign in the MIPS ISA is a register that we're referring. This is a convention, right? So simply, this is an address. I go to the memory, I read data, and then I store that data into RT. So it's our destination register. Good. Exactly. We said at the like if you go 5 slides back, we said in our register file design we have 32 registers. Yeah. Questions? Yeah. True. True. You can only read 32 bits at a time because your data bus is 32 bits and your register file width is also 32 bits. What if can I support? That's a good question. Maybe I'm following up on this. If you want to operate on 64 bits, what do I do? Right? You do something similar to Intel also supports this, which is as if you logically concatenate 2 registers to represent one set of a variable data, right? And this is, someone can ask something like Python, for example, even in 64-bit machines, you can support a variable length variable, right? Like something that is very large bit, like more than 64-bit. How does this happen, right? Simply, you concatenate logically multiple registers that represent that data, which means if you are reading, you read multiple registers, and if you're writing, you write multiple registers. Good. In case of a store, and we'll do the store and then we'll take a break, okay? So in case of a store, how it's a little bit different than the load? Well, the only difference is, first of all, in our address calculation, it's just exactly the same, right? So if you look into that path here of reading your source, take the immediate value, add both, right? Then simply, I'm calculating the address correctly, so I'm done, right? With the offset of the address, maybe I should also write it to you here. I have RS plus immediate. But in case of a store, I don't read the data. In case of a store, I'm taking RT and I'm writing to the memory, right? On that address. Good. And this is where it becomes different than the load. So after you calculate your address here, you feed the address port with your address out of the ALU. But now I'm writing something from the memory that I'm reading from my register file. What do I read? I read RT. So RT right now is not a destination. RT becomes a source. You see that? So you are using the path that is similar to the add, where this location was in fact a source, right? Okay. So in case of a load and immediate add, this was in fact a destination. In case of a store, this is a source, similar to the normal add operation, right? So this is why you take that path for the store, source 2. And now, source 2, if you are feeding the address of source 2, this is the read of the source 2. So the data comes here. This is why we're adding this red line. Why I'm adding this red line? Because I want this red line is in fact that red line here, right? Oh, apologies, it's this one. It's taking RT and writing it to the memory. So simply RT becomes here, which is your second source. You read the data. If you are doing an add, then this is a source where you're going to add to another register. So you go to that path. But if you're doing a store, you take it directly and write it to the memory. Good. So this line here is your store line. Sense? Someone can ask then, I'm adding this line as a hard wire without any mux or anything, but I'm only using it in case of a store. How this is going to be correct? Yeah. In the data memory, exactly. Thank you. So there is a write enable from the memory where it's okay to send data to the memory if you're not enabling the write enable. So the write enable signal is the one that is going to be only enabled in case of a store. Okay, so it's okay to keep this as a wire. The data is always there, but then simply write enable is not really working. Good. If we think of an advanced design, this is in fact not very optimal because you transfer 32-bit on wires. There's a power consumption, right? Not really needed. So you can really gate it earlier. But here we're talking about a basic functionality, right? So I leave it as is, and we're only enabling the write enable in case of a store. Good. Anything else remains the same as the load, because your address calculation offset, which is this whole circuitry here, remains exactly the same. The only change is taking the value of the second source and write it to the memory, because in case of a store, you are writing to the memory. Good. So if there are no questions, let's take a break for 10 minutes, and we start at, 9:45. Hey. Okay, so we stop here. We said that for the store, you need to simply add a path from the second input register, which is this one, your data memory. And also remember that in the store, I'm not writing anything to the register file. So you have to disable the write enable signal for the register file and enable the write enable for the data memory. Okay? Now, after finishing these, oh, by the way, I uploaded the slides to Avenue. Thanks to Arjun. So you can use them to take notes. One thing just to pay attention to is that there are some announcements. Ignore these ones; they are from last year, right? And after lecture, I'm going to upload the updated 2024 one. So what we had so far is add from the archive, add I from the immediate type, load and store from the memory type. Now we discuss the branches, right? Branches have always been a very interesting instruction because, and we will see this a lot in pipelining and superscalar and out of order. And the main reason is they change the control flow of the program, as we said earlier, right? They force you to stop executing your sequential flow and go to somewhere else in the memory. So you will observe from that control logic here, from the changes we make to our control and data paths, that these are the only instructions that forces you to make a change to your fetch unit, right? Not to the execution and the data memory, but rather to the fetch unit. Why? Because they need to update the program counter. If you want to simply understand branches and jumps, you have to always think that their immediate effect is impacting the program counter. Arithmetic instructions, their immediate effect is to impact the register file. Loads and stores, well, different. Load impact is to change the memory, while store impact is to change the memory. Load impact is still to change the register file. Good. Now, if we want to support branches and we're making our instruction to be BEQ, branch equivalent instruction, what do I need to do? Again, I need first to refresh my mind from reading the ISA. What does this instruction really do? It does compare simply RS and RT, so that's the semantic. If they are equal, I need to load the program counter with the new target address, right? Which is our immediate value here after sign extension. If they are not equal, what do I do? Just simply keep doing program counter +4 that you have been doing from before, right? Now, how do I know whether they are equal or not? You need to use the ALU, right? So you either do a subtraction or you need some sort of comparison in the ALU to be able to compare these two values, which means these two registers for you work as sources from the register file. So you have to read them from the register file. So in that case, for the BEQ, I'm reading the two sources here, RS and RT, as two inputs. And then I'm comparing them. Let's say the way I compare them is I subtract them. If they're equal, I have something called zero flag from the ALU. If the zero flag is triggered, it means the subtraction result is 0, which means that two source operands are equal. In that case, I take that zero flag, which tells me that your condition is true, right? And then I use it as an enable to update the program counter. Okay? So if the two operands are equal, the zero flag is 1, which means I have to execute, the branching. How do I execute the branching? Simply, we have our immediate value that we're going to sign extend. We discussed this in a lot of detail last lecture. We sign extend them, and then we add them to the program counter +4. So where does this logic happening? Well, here, you take your immediate value from here. After sign extension, I'm doing something here which is just basically shifting by 2. Why I'm shifting by 2, we'll discuss last time, but I'm going to revisit, but we'll ignore this for now. Simply, you have your sign extension, you have your program counter plus 4, which is coming from the normal path, and simply what I have to do here. What is this thing? So I have my immediate value sign extended. I have my program counter plus 4. What operation I do between them? I have to make sure I didn't lose you, right? Sometimes I ask very simple questions, but just they're part of the flow, right? You have a branch. You compared your two sources. They are equal. So you must jump. How do you jump? Take the immediate value, you add it to your program counter because the immediate value works as an offset. So now if I have the two, I have the immediate value of the program counter, I need to add them basically, right? Now for this add, I could have just pretty much used the original ALU, right? Which is, I already have one ALU in my data path. Why I didn't do that? Why here we are adding another small ALU for addition? Because simply you have already used your ALU during the branch, right? You have already used it to subtract the two values, right? So reusing the ALU again, remember that we don't have any, it's just a pure single cycle access. You want to make sure you only use every function unit once, right? If you start by aligning things, yes, you can reuse it, but the problem is it will also add delay. And because this can be a very simple ALU only for addition, remember that in Amdahl's law, our performance lecture, we said we make the common case fast. How many times we need to add an offset to something, right? If you have any branch, you should do this. If you also have jumps, sometimes you might need to do this. If you have residual jumps, like function calls, you also need to do this. In the reality, in store and load, you do this, but in store and load, you do it once, you can use the normal ALU. But simply, if that's very common, and in fact, branch instructions or control flow instructions in your program are very, very common. You have loops, you have conditions, you have function calls, and because it's very common, I want to make it fast. So I add its dedicated ALU to do that addition, right? So again, I take the immediate value after sign extended. I take the program counter, and then I add them up. This represents my new program counter. Now, under a branch, I take this new program counter and update it in the original program counter, right? Only if my condition is true, right? And here comes this AND gate that work as an enabler, right? You only enable that mux selection line for picking up that new offset plus program counter if the zero flag is enabled, right? And in that case, you select that line. If it was a branch and simply the zero flag is not enabled, what do? You do nothing. You just pick up the old normal path, right? As if this circuitry does not exist. You just take that path. Now this is an AND gate that one of them takes the zero flag. What do you imagine the other one to be? This line is what? Opcode to say that this is a branch, because zero flag can be triggered if you have a subtraction operation, right? So you don't want to really jump if you just did a sub and the zero flag is just suddenly triggered, right? So your condition enabler here is you have a branch and the zero flag is enabled, right? So in that case, I take the new address and then load it to the program counter. Make sense? So this whole circuitry here is just to enable the branch. Now we go back to this shifting by 2. Do you remember from Friday lecture, what is the shifting by 2? Yeah.
There's only 26 bits per jump, so that you have to like get rid of the first 2 bits, I guess, in this case, because you can't jump more than that, like that distance away.
True. Yeah. Aside from the starting point about that, the jump is really here we're having a branch, so we only have 16 bits, right? But the rationale remains the same. Is that simply we are branching or jumping in an instruction granularity, which is 4 bytes, which means you don't want to change the first 2 bits of the program counter, right? Because 4 bytes would need 2 bits for an offset. So you just ignore the first 2 bits. So you shift your immediate value by 2. Good. Makes sense? Questions? So if you implemented this and you want to support branch not equal, what do? A very simple thing to add to that circuitry to support branch not equal. Yeah, an inverter, right? Or a not get exactly. It's like here, instead of the zero flag you enable, if the zero flag is not enabled, you basically just do the branch should equal, right? So just think about this thing. If you want to support other type of instructions, what is the minimum gates or the minimum circuitry you add on top of it to support that? And here, because you want to support both branch not equal and branch equal, what do I need to do? Well, simply maybe whether I take the not or I take the original zero flag, I need a mux, right? And in that case, this mux will select whether it's P and E or BQ. Good. What if I want to support branch greater than, branch less than, etc., etc.? There will be some circuitry here that takes maybe some other some other flags, right? And then gives you a selection line that determines that. Good. Questions? So as I said, you can observe here that the branches, unlike the other instructions that we worked on so far, that have been changing this part and this part, they mainly change the fetch unit, right? Updating the program count, right? Good. Okay, now adding on top of branches jumps. This makes also this fetch circuitry a little bit more complex because right now I added all of this green thing is for the branching. But now for my jump, remember that in a jump, you don't have an offset that you add to the program counter. You just take the jump address directly, sign extended, shift it by 2, and load it to the program counter, right? So what would happen is, again, remember this is the logic we have. You take these bits, which are your immediate value. Well, this one, sorry, you shift left by 2 to basically do this, well, 4-byte instruction thing. And then you simply take the last 4 bits of your program counter, because you have 26, 28, and then 4 bits of your program counter, and you load it to your program counter. How do I do this? Well, I take the immediate value, and then I shift it by 2. I go here. Well, ignore the mux for now, assuming that we only have a jump. So I continue with this, but I need to simply add the last 4 bits of your program counter. This is your dashed line here. It assumes that you take the last 4 bits of your program counter, augment it to your 28 bits of your immediate value jump after shifting by 2, and then you load it to your program count. Now, because I need to do this only if this is a jump, I also need a mux. This mux is going to pick from this one, or if it's a jump. So this selection line, you can imagine that it comes from the control unit. If it's a jump equal 1, I take the red path. If it's a branch or a normal one, I take that path, right? So we have concatenated muxes here. So maybe if we stop for a second and reflect, and we have the 3 types. Let's start with the simplest one. No branch, no jump, nothing. Program counter plus 4. What path do I take? Well, simply I have program counter plus 4. I go to that line. I go here. My selection line, because this is a normal add instruction, for example, is going to be 0. It's not a branch, so I pick that one. And this one here, it's not also a jump, so I continue with this one, and then I load it to the program counter. Right? It's very simple. Now, if I have a branch, then this mux will enable the second path, right? And assume that the branch is taken. Taken means the condition is true, which means also there is an enable here. In that case, this path will be ignored, and I will take the branch path here, and then the branch path will be loaded here. This was a branch, which means it's not a jump, so I continue with that path and I update the program counter. What if it was a branch, but the condition is false? In that case, this enable will also still be false, which means you take the normal path back again. So you go back to case 1. Now, if it's a jump, well, everything here calculates simply. It's not a branch, so you take the first path, you load it here. But this is a jump, so your selection now will be the second one. So you ignore this one, and you go for the second one and load it to your program count. Is that clear now? So you have 3 cases, but in reality 4. You have the normal program counter plus 4. You have the jump. You have the branch if the condition is true, and you have the branch if the condition is not true. In case of a branch, condition is not true, or normal path, you just increment program counter plus 4, which is happening here. In case of a branch, a condition is true, you load in your added offset to the program counter. In case of a jump, you take the immediate value directly and load it to the program. Questions? Is that clear enough?
Is that going through the shift register? Or is it just like direct?
Yeah, no, it's not going through the shift register. It's just simply you take the last 4 bits of your program counter register and augment it. So here, that path is only 28 bits. Its width is 28, right? Because remember, we had 26 plus shifting by 2, so it's 28. So you still need 4 bits from the most significant bits of the program counter. And you just basically, it's just adding them to concatenating them in RTL. So this dotted line here is just 4-bit wide, like 4 wires, taking the last 4 bits of the program counter from here and augment it to the 28 bits such that you end up, so if you want to write it precisely, you say that this is 28, this is 4, and this is 32. Make sense?
Yeah.
So a simple RTL concatenation. Any other question? Yeah.
Same reason as
Yes. Okay, so now supporting other types of instructions should be pretty much adding simpler circuitry because we took the main types of instructions that adds most of the complication and the differences. Supporting others can be simple. Good. Now, putting it all together, we have been saying along the lines of, okay, there are selection lines. This is how our data path looks like. But we never said how do we calculate these selections line, right? So if, for example, like I need to build this circuitry of the control unit, what do I need to drive, right? From what we discussed so far of our types, we said the register file, you have simply a write enable here, right? Because in case of a store, I simply have to disable the write enable. I'm not writing to the register file. In case of all the other types we had so far, well, even in case of a branch also, you have to in fact disable the write enable because in branch instructions, you don't write to the register file. But in case of an add I, and load, you are writing to the register file. So this write enable will only be enabled for instructions that write to the register file, right? That's the first thing. Then we have this mux here that simply determines our register file destination, from where should it come in the field of the opcode. In case of an add, it comes from a location. In case of an immediate and load, it comes from another location. And here in this multiplexer also, we said the second source of the ALU, should it come from the register file or it come from the immediate value, right? And this is a selection line here that we call it ALU input B. Now, what type of operation I do for the ALU? In case of an add I, and load and store, I'm doing an addition. But in case of a branch, I'm doing a subtraction, for example, right? So you need an ALU op control. Here in your data memory write enable, when this should be 1, there's only one instruction that writes to the memory, yeah? Store instruction. Anything else, this is just ignored. Now, picking up that path from the memory and updating it to the register file, so there is a mux here. This mux is when there's only one instruction reading from the memory, which is the load, right? So this one will take that path if it's a load, otherwise just any other instruction will take from the ALU output. Good. And all this mess here is related to branching. If you have a branch, this is 0 flag, and then if this is a jump. Good. Now, we go through our instructions one by one and see the values of these bits, because again, our final goal is to build the circuitry that drives these values, or to build the control path, right? To build the decode unit and enabling the selection lines. In case of an add, what values do I need to drive here to make sure that the add operates correctly? We'll take it one by one. First of all, does the add write to the register file? You think? Yes, definitely, right? Both add and add are to the register file. So you have to do the register file write enable to be 1. Now, in case of our add instruction, for this destination 1, which one does it read? It reads that second source, or it reads the actual destination in the output field. Remember that in our add, we had 2 sources and 1 destination, right? We had add, we can call it, well, RD, and then RS and RS, right? There are 2 sources and 1 destination, which means source 1 and source 2 are used from the opcode as real read operands, and the third field comes from the real destination, right? So in that case, I need to make this selection line to come really from the real source. Remember, you can put in the opcode in front of you. There is the opcode, the function. There is, I will call it source 1 at the moment, and then source 2, and then there is the destination, right? So here, I want the add to pick up the destination from that field, right? Which is going to be this red line here. So I need to enable the R destination to be 1. In case of an add I or load or etc., it should just come from here, right? Good. So we continue. In case of an add, among these two paths for this selection line, which one should I pick? It will definitely should be the one coming from the register file because you have two sources, right? So in this case, you pick the first line, you have the ALU enable the register to be 0, to pick that one. I'm doing an add operation, the ALU, assume that the ALU op is going to be 0 if this is an add. Am I writing to the memory? In case of an add, I'm not writing to the memory, so our memory write enable should be 0. Also, I'm not reading from the memory in case of an add. So in that case, the read, register file destination from the memory, the mux here should just pick the normal ALU path, which also should, this selection line should be 0. I don't have branches, I don't have jumps and an add, so simply everything here, every selection should be 0 to pick up the normal activated path of program counter plus 4. Good. So going back through this, 3, 6, 8 signals, you end up simply with your R destination is 1, register file write enable is 1, everything else is 0. Make sense? Okay. If we pick up the store, on the other hand, a different type of instruction, what do I need? First of all, in a store, am I writing to the register file? No, you are writing to the memory. So in that case, your register file write enable is 0 and your memory write enable is 1. Good. So you flip this from the add discussion. Then also in case of a store, it's an immediate type instruction. So you need to read an offset, right? So you need to read an offset and simply and this offset simply comes from, so just remember the storing thing for you. So there is source 1 that you add to an immediate value. You take the address and then simply go to the memory and you write to the memory or destination, right? That's really what you do. This is address, this is data, and this is mem. So you need to enable the write enable for the mem. For our register file operation, I'm having one source, right? So I'm reading that source here. I don't have any destination, so in reality, this is just don't care. Because I'm not writing to the register file. Why is safe to make this don't care? Because our write enable is just 0. There is no destination. So whatever you have here is no way to impact your register file. And then I need to take that path, but this path is just a wire, so it's always there, right? So I don't need to worry about it. And then I'm not really reading anything from the memory, but I'm making this as don't care. One, making it as don't care. Because again, this path will go eventually to write to the register file, and I'm disabling the register file write. You can observe from here, we're trying to make our logic as many don't cares as we can, because remember from 2DI, this will simplify your Karnaugh map, right? This will give you more possibilities. It can be either 0 or 1, you don't care. In case of a store, you don't have jumps and you don't have branches, right? So you should be fine. In case of a store, I need to simply, for this kind of selection line, I'm adding two things together. I'm adding this source, which is source 1, but I'm adding an immediate value. So for this mux, your operand doesn't come from the second operand doesn't come, which is operand B, doesn't come from the register file, but rather comes from an immediate value, which is sign extended. So you have to really flip this to be 1 to take that path. Good. But you are still doing an add operation, so your ALU op should still be 0. Yeah, Arjun. Yeah, well, if you are really not taking that branch path and you are disabling it, no matter what happens here, you don't really worry about it, right?
It doesn't need a control because the mux that
It gates it, exactly, right? So it's only being used if it's a branch. And if it's a branch, you are sure 100% that this path is sending a valid data to the ALU, which means if this is always adding, it's fine. Okay. Other questions? Good. Okay, so in case of a branch, which is a third possibility, Yeah, I'm having a lot of writings from last year. You can ignore them because really I was explaining what happened with the branches, for loops, and different that, but that's fine. So let's focus on the signals themselves. And again, we take them one by one. In case of a branch, am I writing to the register file? No. Again, what do we do for a branch? You simply have two sources. Then you have an immediate target offset here. So you read these two sources and compare them, which means you never write to the register file. You in fact update the program count. So in that case, write enable for the register file should be 0. What about the memory? Am I writing to the memory? In case of a branch, I'm also not writing to the memory, so write enable should also be 0. Now we go to the sources. Here I'm using the two sources for the BAQ. So this both should be used, and both should be fed to the ALU, which means for this mux, I have to set it to 0, similar to the addition operation, right? Because I need to read that back. This is RS1, this is RS2. Now, for the ALU, it becomes a little bit different than the store and the add, because I'm doing a subtract operation. So you'll see that the ALU op becomes 1 to subtract these two. Good. And because this is a branch, you simply have your this thing branch equal 1. It's feeding to the AND gate, right? And the second one is the 0 flag, just doesn't have any control. It's not a jump, so the jump is 0. And then because you are not really reading from the memory as well, so this one is don't care, because whatever you do, you are disabling the register file. Good. So I guess the discussion for the last 10, 15 minutes has just went down to a pure digital design discussion, right? After we have articulated the high-level design of our logic and data path, how do we design the control path? Finding out what we're building here in one by one, if you didn't observe yet, is just the truth table of these 8 signals or 9 signals, right? And why do I need to come up with them? It's just simply because we need to design this control unit, right? After I come up with all the possible bits, don't cares, and truth table, I need to build the circuitry that feeds them from the opcodes, right? So your output will be these signals, your input will be the opcode and the functional from the actual instruction itself. Now, how do we implement this? If you are doing this in RTL, there are multiple ways of implementing this, but there are 2 major ways that are common. You either build this as a very simple, again, coming from 2DI, I had a truth table, I build the circuitry, AND gates and OR gates, or you basically store this in a lookup table, right? That is addressed by the opcode, and the actual values are stored in the lookup table, right? Good and wrong. Good. Every design option has a trade-off, right? Scalability versus performance versus area. But at the end of the day, you want to implement something like this, right? So if you have a lookup table ROM and you have all your signals that we had so far, your input will be your opcode, because the opcode is the one determining whether it's an add, an I, all our 6 types of instructions, and the output will be this one. Right? You will observe that from this truth table, we have transformed some of the don't cares into either 0 or 1 to simplify the design, right? But there is an earlier version of that table that simply has the don't cares. Then you do the reduction later on. Good. So whether you do this as a ROM or lookup table or an actual logic circuitry or logic gates, I guess it's a very simple exercise, right? We can give to the second year students as a midterm question, they will be able to find very easy, right? Great. Here's some discussion on really what is the trade-off. If I have really a ROM and I'm only supporting 6 instructions and 9 control signals, it's very easy, very small lookup table. But what if you have hundreds of instructions and a couple of hundreds of control signals? Your area might be large. So you need a large ROM in that case. And what would be the access time to look up that thing? Is it a single cycle? Is it simply a couple of cycles? It will also impact things, right? Scalability. On the other hand, if I'm building this in a combinational logic, it can be optimized, but also it's prone to error because it can be very complex. So you have to verify it well. Yeah. Here's some examples of, well, in a real 32-bit machine, you might need around 4 kilobytes of a ROM because you already have more than 30,000 control bits, right? If I'm building this in a combinational logic, again, very simple code. I only have 6 instructions in our case. The branch is just coming directly from the branch, the jump coming directly from the jump. Memory is only coming from the store, right? So just direct one signal, and also the subtraction is only coming from the BQ. Like the thing to focus on, this is very simple because you're only doing 6 instructions, right? But if you have a subtract, then this will not be as simple as this, right? You will have to do some logic here. But just give you some taste of how this can be designed. Great. So far, time is over. Yeah, and the exception is a very interesting topic, and again, it will become more complicated for the pipeline. So I will stop here, and tomorrow we can start. Thank you.